Good day everyone and welcome to these lectures on adsorption units, operations which are used in the physico-chemical processes for water or wastewater treatment. So, in the previous lecture with respect to adsorption, we studied adsorption kinetics, adsorption isotherm, and in the adsorption kinetics we found that there are different types of kinetic models which can be used to represent the kinetic data. Similarly, in the adsorption isotherm we studied there are different types of isotherm equations like Freundlich, Langmuir, Redlich-Petersen, Temkin etc., which can be used to represent the equilibrium data under those conditions. So, Freundlich and Langmuir isotherms are one of the basic isotherm equations which are used, and there are like 2 parameter model equations, that means only 2 parameters are unknown in those equations. Now, continuing further, one of the equations which is commonly used is called BET. So, before going to BET, we will try to understand what is monolayer and multilayer adsorption, and after that we will try to discuss how the BET theory has been developed and how the BET theory has been applied for determining the important adsorption characteristics using the isotherm equation. So, this we are going to learn today. So, surface area, pore size which are determined for any adsorbent, they are determined by understanding the nitrogen adsorption studies or any other inert gases studies, adsorption studies on various types of adsorbent. So, before going towards that, let us understand the monolayer and multilayer adsorption. So, in the chemisorption, in which there is a electronic interaction between the adsorbate and the adsorbent molecules, only a monolayer of adsorbate can be formed on the adsorbent surface. So, this is there because there is a bond which is occurring. Now, and that bonding is not possible for the second layer. If any second layer will happen, that will not be bonded by any electronic interaction, it will be only physical in nature, and that will be by van der Waals force of attraction. So, this is for chemisorption only single layer is possible. Now, for physisorption where van der Waals forces of attraction are important only, the first monolayer formed on the surface of the adsorbent can act as an adsorbent surface for next layers. So, in this way we can have a multi-layer adsorption which is possible because only van der Waals force of attraction is operating. So, in chemisorption only monolayer adsorption is possible, in physisorption multi-layer adsorption is possible. If any multi-layer adsorption is occurring, so there are only 2 possibilities. One possibility is that all the layers are multiple, only physisorption is occurring. In the second case, the first layer may be chemisorption and the subsequent layer, if formation occurs, will be physisorption, but these can be determined only from experimental data. And for analyzing this multi-layer adsorption, BET is one of the common isotherm which is used for determining this. So, what is BET? So, for multi-layer equation we have BET equation. So, BET equation, BET theory was given by Stephen Bronner, Paul Emmett and Edward Taylor in 1938. So, that is why Bronner Emmett Taylor theory. So, this is BET theory or BET equation. It was further extended by it was extension of Langmuir theory which was developed in 1916. So, as per Langmuir theory, the monolayer adsorption of gas molecules on the solid surface of a to the gas pressure of a medium above the solid surface at a fixed temperature is given by this expression, where theta is the fractional cover, P is the gas pressure and alpha is the constant. We are discussing this equation in particular because any of the adsorbent properties with respect to the specific surface area, pore size etc., can be determined using the nitrogen adsorption. So, nitrogen is a gas. So, that adsorption is generally done on the adsorbent surface, and for analyzing the data this equation is used. So, that is why this discussion is being done. Now, suppose S0, S1, S2, S3 etc. are the surface area covered because of different layers of adsorbed molecules as shown in figure. So, the total area of the adsorbent therefore can be obtained by summation of the individual surface area. Now, the BET equation is given by this particular expression which is given here, and in this case the relative P by P0 which is called as relative pressure is important. So, here the equation has been converted in such a form that it is linearized already. So, what does it mean here? That generally this all these parameters will be known and this P by P0 will be known. So, slope will be this and intercept will be this. So, from this we can determine a number of parameters. Now, within this equation Vm represents the volume of gas adsorbed when the surface is covered with a complete unimolecular level. So, we try to analyze the data with respect to monolayer only, okay, but we extend it for multilayer. So, this is there, and for Langmuir theory the saturation is, if we plot QV versus C data, as per Langmuir theory the saturation will occur. So, this is like a monolayer. So, this is first, but if the extension is there, so we will analyze the data only up to this point. So, this is the first monolayer formation has already occurred. Now, monolayer coverage is determined using the BET equation. So, the this particular thing is plotted versus as a function of P by P0, and the plot is linear in the range of generally it will be in the range of this, it may vary also, but we use the only the linear range data. At higher relative pressures the BET plot may deviate from linearity as non-ideality and pore condensation etc. may start occurring at those conditions for gas phase adsorption. So, we do not consider, we only consider data up to the range where the linearity is more, and generally it will be up to the relative pressure range of 0.3. Now, slope and intercept from this plot can be used for determination of monolayer capacity, okay, which is Vm, and then the intercept and slope can be determined. So, this we can see here the intercept and here the slope. So, and then the if we actually little bit manipulate, so we can find out the value of Vm from combining these two equations. So, this is possible. So, from one we can find out the value of C, and if we keep it in this, so like we can keep like intercept, suppose it is I. So, I by C Vm, and from here the C value is 1 upon I Vm, okay, and in the second equation slope S is equal to C minus 1 upon C Vm, okay, and we can keep the C values here, or we can directly keep the, in place of C we can keep the Vm values from here. So, this is because we need to find out the Vm. So, if we keep Vm here C minus 1 and C, and Vm is equal to 1 upon IC. So, C goes off. So, and S into I is equal to C minus 1. So, C is equal to 1 plus Si. So, this is the expression, and if we keep here and solve it, we will get this equation that Vm is equal to 1 upon slope plus intercept at STP values. So, we can find out the Vm values whatever is the monolayer volume which is there. So, this expression can be used for finding out the pore surface area. Now, first for determining the adsorbent property like pore surface area, we first thing that why we use any gas. and which gas is preferred. So, what we do is that there are few options. First thing, for determining surface area, we should select the gas which should have some properties. One thing is that it should be inert, that so that there is no chemical reaction occurring, and we are going we can, it does not react with the adsorbent. So, inert gases can be used. Now, inert gases can be helium, nitrogen and others. Now, among it should be having lower possible molecular size. So, lower molecular size is preferred. So, and if this is there, we can determine more accurately the surface area. So, this molecular size should be lowest possible. Now, the lowest possible will be helium, but with helium there is a problem that the gas separation from the atmosphere will be difficult. So, this gas is costlier. Second thing is that we have to, generally the apparatuses are determined with respect to liquid nitrogen condition, where we can adsorb maximum amount of nitrogen. So, what we do is that we take the temperature to a certain level where nitrogen is in the liquefied form. So, for this so that the maximum nitrogen adsorption may occur. So, generally nitrogen gas is preferred because it is easily available, it is inert also, and it can, its pore size if is good enough for analyzing any gas separation or otherwise. So, this is possible. Most of the gases which are there have higher molecular size. So, generally it will be good enough for gas phase separation, for liquid phase separation always it will be good enough. Okay. So, now the total number, for suppose we are performing calculation using N2 molecules. So, the total number of N2 molecules adsorbed corresponding to monolayer volume Vm can be calculated using this equation. So, number of molecules is equal to Vm, Vm will be in meter cube. Now, the molecules, what we do is that we know that at any standard temperature pressure conditions. So, any 1 mole of gas occupies 22.414 liter of volume. So, that 22.4 has been converted into meter cube. So, we have 0.0224 meter cube per mole. So, this meter cubes go off, only mole is remaining. Now, each mole we know occupies 6.023 into 10 raised to 23 molecules per mole. So, this mole also goes up. So, we can determine the number of N2 molecules which have been adsorbed if we know the Vm. So, this Vm can be determined from the BT equation, and once Vm is known, we can determine the number of N2 molecules which have been adsorbed on the adsorbent surface. So, this can be determined. Now, each adsorbed N2 molecule occupies an surface comparable to its cross section, and that cross section is 0.162 nanometer square. So, this is there. So, that is how if each of the N2 molecule occupies this, and from that data we can determine the surface area. So, surface area will be Vm, what we do is that we multiply for each of the molecule. So, each N2 molecule occupies this surface area. So, what we do is multiply here 16.2 into 10 raised to minus 20. So, once we get this, we can use this particular equation to find out the surface area for any adsorbent. Only thing is that we should know the Vm, what is the monolayer volume which has been adsorbed, and that data can be obtained from the BT equation. So, this is possible. So, all the calculations etc. have been performed here. So, 4.36 into 10 raised to 6 into Vm, and this Vm should be in meter cube. This we have to take care. Okay. Now, This is the apparatus which has been used. So, this is available with us also. So, this is from Micrometrics. There are many other companies also, and what we get the data, we generally what we do is that we get this type of data: quantity adsorbed centimeter cube per gram of adsorbent at STP. So, for gas phase separation we always whenever gases are involved and whenever we are reporting any volume, we should always report the temperature and pressure also. So, common thing is use standard temperature and pressure. So, triple point of water conditions have been used for reporting the quantity adsorbed. Now, and relative pressure is in the range of P by P0, and so this type of apparatus can be used for performing this test. And in this we get, what we do is that first we adsorb the molecules and then we dissolve the molecules. So, adsorption is represented by this curve, you can see here, and then dissolve. And not only we can use the adsorption and desorption data for calculation of surface area, we can interpret many of the things using this particular curve, which is like QV versus P by P0 curve, and how, what is the behavior of this isotherm, what is the hysteresis type, they give lot of information. So, many people work upon this, and from this data we can get this type of data also, dV by dt. I will not go in that much detail in this lecture, this is another topic, but we can get the data that okay, that how much surface area is available with respect to up to 5, suppose 5 nanometer we can see, up above that. So, any of the size range we can select to know that how much surface area is because of mesopores, how much surface area is because of micropores. So, all those analysis can be performed. Now, this is the cryogenic container which is used for filling this liquid nitrogen, and this liquid nitrogen is filled here, so that we can keep the temperature up to liquid condition, and then nitrogen is flown, okay, and so that the maximum amount of adsorption may occur, and after that desorption studies are also performed, and the quantity adsorbed or dissolved are measured at various conditions using the calculations already there in the software itself. So, let us take some numericals related to this, so as to understand. Now, nitrogen was employed to determine the surface area of 1 gram of sample of silica gel, and results obtained are shown in table here. The sample silica gel was maintained at the normal boiling point of liquid nitrogen. So, we always maintain the temperature of 77 Kelvin in this unit. So, this is very less. Now, one molecule of nitrogen occupies 16.2 into 10 raised to minus 20 meter square of area of plane surface. So, this already we have learned previously. Now, calculate the specific surface area of silica gel using the BET method, and the saturated vapor pressure of nitrogen at 77 Kelvin has been given to be this, and the equilibrium pressure at different conditions are given at 5, 6.3, 7.5, 9, 11.2, and here actually the data points may be large number, only for numerical only few data points are given, and then the volume of N2 adsorbed at this condition has been given like this. So, this data is available. Now, what we do is that this is the BET equation. So, we perform the calculation first. So, volume is already given, okay, pressure is given, P0 is known, it is given. So, we determine P by P0. Similarly, we can determine P by divided by V into P0 minus P. So, or this can also be written as 1 upon V or P by P0, this is there, and 1 minus P by P0. So, this equation can also, because P by P0 is already known, V is known, so we can determine this. So, this is y axis data, this is x axis data. So, this is there. So, we plot this data. So, this type of equation will be there and its equations are given. So, this is plotted as a function of P by P0 and this is given. Now, once this is given, what we do is that we use this data with respect to perform other calculations. So, what are those calculations? We know that intercept is 943.5. So, this will be there and slope is this value. Now, monolayer volume, if you remember, it was given here that it is equal to 1 by slope plus intercept. So, this is the same is being done here. So, 1 by slope per intercept, because both are having the same unit per meter cube. So, because 1 by this is being done, so overall unit will become meter cube. So, Vm is 7.2 into 10 raised to 6 minus meter cube minus 6 meter cube. The surface area can be calculated, it was already done previously. So, this data has been used here, and since each of the molecule is having this much area, we can perform the calculation, and surface area is to be, for this particular condition, it is 31.4 meter square per gram of adsorbent. So, this is the surface area which has been obtained for this. So, this way we can determine the surface area, we can determine the average pore size etc. also using this equation. But now another data has been given where at different pressures for a catalyst, this data has been given and the vapor pressure has been taken here in millimeter Hg. So, and these values are also in millimeter Hg. So, any of the units may be there and these values are there, and the volume of N2 adsorbed in centimeter cube at NTP per 100 gram of catalyst are given here. So, the catalyst is 100 milligram it must be of the catalyst. So, this P by P0 data, again P by V into P0 minus P data has been determined. We can plot this data and we draw a linear line on this. So, slope of this curve is 0.0269, intercept is 0.0184 and both can be used together to find out the volume, and once the volume is known, because the surface area is known, we can determine the calculation and the overall surface area will be 9637. So, centimeter cube per gram, and sorry, this can be used for directly determining this value 96.37 meter square per gram. So, this is there, and through this we can determine the surface area. Now, along with the surface area, there are different classification of adsorption isotherms, in particular for gas phase adsorption, and they have different characteristics and we can interpret lot of data out of them, and there are different classifications like type 1, type 2, you can see here type 3, type 4, type 5 and type 6. So, there are 3 classifications which have been given for different types of isotherms, which can be observed for any gas phase, and they give lot of data for gas phase or liquid phase also. So, first is type 1, which will be like very similar to Langmuir. So, here the saturation is being reached. So, this is called type 1 isotherm. It is concave to P by P0 axis, and if it is there, it will exhibit that this particular thing has more microporous structure. Now, there is a possibility that the curve may go up to saturation up to this, and again it is going up. So, this is called type 2. So, this is also very common. So, this is exhibited by nanoporous, non-porous or microporous solids. They have unrestricted monolayer or multilayer adsorption which is occurring. Point B indicates relative pressure at which monolayer coverage is complete. So, this is there. So, this is possible for any gas. So, pores are for type 1, pores are typically microporous, okay, with exposed surface residing almost exclusively inside the micropores, and which once filled with adsorbate they reach saturation. So, this is there, and they leave little or no external surface area for further adsorption. In type 2, it is most frequently found when adsorption occurs on non-porous powders. So, this is possible, and it is like multi-layer it is happening. So, it is like van der Waals forces of attraction. Inflection points occurs to the on the completion of first adsorbed monolayer. So, this is there. Then there is a type 3 which is convex to the P by P0 axis, we can see here it is going up. So, it is again for non-porous solids. Type 4 will have again, it is starting to go up, then saturate and again go up. So, initial part of the type 4 follows the same path as type 2, but later on it varies. So, it is more exhibited by mesoporous solids. So, this we can see. Similarly, type 3 already we have discussed. For type 4, this is the type of, they will reach some saturation and again increase very quickly from here to here and again reach the saturation. So, this is not commonly observed, it will be exhibited by mesoporous solid, but generally not very common. And type 6 is also not very common, but it may have multiple saturation levels which are there. So, this is there, and from this type of curves we can get the idea that okay, which type of isotherm is there, and from that also we can interpret lot of things using whether it is porous, non-porous, what is the tentative, whether it is microporous or mesoporous. So, some idea can be obtained from initial curve itself without performing the calculation, and few of the curves are not very common like type 5 and 6, but initial curves are first, second, third, fourth are common more. So, and also because we perform the adsorption and desorption. So, during adsorption it will go like this, but in the during desorption it will hysteresis will be there. So, hysteresis, if any of the system or adsorbent shows hysteresis, it means that there are more mesopores. Hysteresis gives information regarding the pore shapes also, which will be shown in the next slide. Type 1, 2, 3 type of isotherms, they are like generally reversible, but type 1 can have more hysteresis, and type 4 and 5 always exhibit hysteresis. So, this is possible. Now, depending upon the type of hysteresis and type of curve, different types of pores are possible. So, earlier we had discussed there are different types of pores possible like cylindrical, conical, bottleneck, slit shaped, and different types of hysteresis behavior. Type A hysteresis behavior, you can see the difference is coming, and this will sluggish. So, there is a S shape is there. For type B there is not a very pronounced S shaped, it will diminish very quickly. For type C this is more linear type, and this is the shape we here. Similarly, for type D there is a difference, type E. So, each of the curves show different types of hysteresis, and from hysteresis data we can interpret lot of the pore type which may be available. So, they may be cylindrical, slit, conical. I suggest that you can read any of the references which are given here for better understanding this hysteresis and different type of isotherms shapes, because they give lot of information, but we need to study them in more detail for understanding. This is only a basic information has been given. If you are interested, you can go on reading this literature for better understanding. So, this will now close today's lecture, and from today's lecture we found that okay, nitrogen adsorption is one of the common methods which is used, and we get lot of data with respect to how much volume of nitrogen has been adsorbed at different relative pressures. So, once that data is available, we apply the BET equation to determine the surface area of the adsorbent. There are many other possible calculations which are beyond the scope of these lectures, and which are possible, and those data can be used for performing the determining the pore size, whether they are micropores, mesopores, macropores, how much percentage of those pores are there, this is also possible. We can use that same data to determine the heterogeneity of the adsorbent surface. That information can also be collected, but this can be determined using this can be understood by reading different literatures which are there. So, with this we will end today's lecture. Thank you very much.